Alright, so last time we talked about heat. So today we'll start talking about work, the other way that you transfer energy. Okay, so what's work? Work is defined as force applied over a distance. So if you apply a constant force on an object and it moves a certain distance d, then the magnitude of the work is just the value of the force times the distance. Okay, so in terms of force and displacement, the vectors work is the dot product of force and the displacement. So F times delta x. Okay, so if force and delta x, if we're just doing two-dimensional systems, so if your force is this way and the displacement is this way also, if they're pointing in the same direction, then that tells you that your system's going to gain energy. So if you have something, an object moving that way, you're pushing it that way, what do you think will happen to it? It speeds up, right? It gains what we call kinetic energy. It gains energy. But if they're all pointing in opposite direction, then you expect the system to lose energy. So if you have an object that's moving that way, but your force is pointing in the opposite direction, what happens to it? Okay, it slows down, it loses kinetic energy. Okay. Now, if your force varies with location, then you cannot just multiply force times distance. You're going to have to do an integration. So what would be your integral? Your work would be integral of force f dx. So f will be a function of x, right? So f depends on location and integrated from x1 to x2. Okay? And geometrically, you can interpret it like this. If your force versus distance is constant, okay, the integral is just the area of that rectangle. It's just going to be f times delta x, right? But if your force depends on distance, it varies with distance, then what do you get? So if this is x1 and that's x2, then the area under that curve is just the integral of f dx. Okay, so you can imagine this as being made up of little rectangles. If you take the limit at very small widths and sum up all of those rectangular areas, you get the integral under your curve. Okay. Work energy theorem. As we said earlier, that if you do work on an object, you change its energy. Work energy theorem says the amount of work, okay, will just be equal to the change in kinetic energy. And you can derive that. You can say, if you remember, force equals mass times acceleration, right? And acceleration is derivative of the velocity with respect to time, correct? Okay. So if you want to integrate f dx, that's okay. So that's going to be integral of mass times the derivative of velocity with respect to time times dx, right? And so that's going to be, I'm going to do the chain rule here. Mass times derivative of v with respect to x times dx dt times dx. Is that correct? Think of these as that will two things that will cancel out. So that's going to be dv dt, chain rule, right? So I can rewrite this integral of, what's dx dt? That's just v, right? Dx dt is just v. And so I'm going to write dv dx times dx. What is dv dx times dx? It's just dv. So this is just integral of mv dv. And we've effectively changed our integration variable from x to v. So instead of integrating from x1 to x2, we're now going to be integrating from v1 to v2. And as you can see, what's integral of mv dv? M is a constant, that's the mass. Okay, so v squared over 2, integrated from v1 to v2. And that's just going to be 1 half mv2 squared minus 1 half mv1 squared, which is kinetic energy 2, final kinetic energy minus initial kinetic energy. So if you've ever wondered why kinetic energy was defined as 1 half mv squared, that's the sort of the justification for it. It gives it the same unit as work. Okay, so you can see that's just the change in the kinetic energy. The amount of work done is just equal to the change in the kinetic energy. All right? So if you have positive work, that means your object has gained kinetic energy, it has sped up. And if you have a negative value for your work, that simply means that's the amount of kinetic energy that was lost by your object as a result of the force applied on it. So let's do an example here. If you have, how much does the kinetic energy of a 1 kilogram object change if it falls a distance of half a meter? And what's the speed at this point, assuming it starts from rest? How would we solve that problem? Okay, so you have an object that falls at 1 kilogram, falls a distance of half a meter. What's the force on the object? Force of gravity. So mg, right? So our displacement is downward. So our delta x is going to be, let's take our downward direction as positive. Okay. So delta x is positive 0.5 meters. And our force is constant, right? It's just equal to mg. So I'm just going to take the positive value, positive direction. They're both pointing in the same direction. So what do we expect? We expect the object to speed up, acceleration due to gravity, in fact, is known to be how much? So 1 kilogram, 9.8. Okay. And did I use 1.00 kilogram? Okay. 9.8 meters per second squared. So that's going to be 9.8 newtons, right? So what's the work that we did on the object? Or that gravity did on the object? Force times delta x, 0.50 meters, times 9.8 newtons. That's going to be half of 9.8, so that's 4.9 newton meters, which is 4.9 joules. That's the work. So that's the change in kinetic energy, right? So assuming it starts from rest, this is going to be your final kinetic energy. So if you know your final kinetic energy, can you calculate your final speed? Kinetic energy equals 1 half mv squared. Right, so v final would be equal squared times 1 half m will give you the final kinetic energy. How do I solve for the final kinetic energy? Final speed. Oops, what did I just do? This thing. How do I solve for my final speed? Vf equals 2 times the final kinetic energy divided by the mass, and you take the square root, right? So it's equal to 2 times 4.9 joules divided by the mass, which is 1.0 kilogram, square root of, that's 9.8. What's our unit? Joule is kilogram meter squared per second squared. And our unit for mass is kilograms. So kilograms cancel out. Square root of 9.8 is how much? 3.1 meters per second. That's the speed. After it's dropped half a meter, it will have gained 3.1 meters per second in terms of speed. Okay? So that's work energy theorem for you. How much work is needed to lift a 1 kilogram object by a height of half a meter? So I have a 1 kilogram object right here. So I'm going to hold it. Okay. And I'm going to lift it up to a height of half a meter. Well, that's a long thing, long hand like that. All right. So I'm holding it. I'm going to lift it up half a meter. How much work is involved there? So what's the acceleration? Average acceleration. It's at rest before, it's rest after. What's the acceleration? Initial speed is 0. It's at rest, right? And final speed is also 0. What's the average acceleration? What's the average force on the object? The average force on the object is also 0. Force equals mass times acceleration, right? So what's the work? 0. As far as the object is concerned, total of 0 work was done. Why is that? If it's not accelerating, then on average the force on the object is balanced. What does that mean? The force due to gravity must be balanced by the upward lifting force that you're exerting on it. The net force on the object, since it did not accelerate, would be 0. It's different if you have an object that's rising. Okay, you toss it up. So as it goes up by a height of half a meter, the only force acting on it, assuming neglecting air resistance, would be gravity. Right here, you're actually exerting a force on it to counteract the force of gravity that causes you to lift it. Now, what's the force that you are actually doing? What's the amount of work you're actually doing? Then you only consider the force that you are exerting. So that means if the average force is 0, the average force you're exerting, if gravity exerts a force of mg going downward, how much force are you exerting? On average, you must be exerting a force of negative mg. If we're taking positive direction as downward, it doesn't really matter which direction you take. So let's say the downward direction is positive, so the upward direction is negative. So the force you're exerting is negative, right? Negative mg. So as far as you're concerned, how much work did you do? Then how much work did you do? Whatever force times the displacement, right? And we'll just take the average force exerted. So the average force you're exerting is negative mg. And what's our delta x? Is it positive or negative? Okay, we've taken the upward direction as negative, right? So we're going to have to put negative 0.50 meters here. Okay. So if that's the height, h, it's just negative h in this case. So negative mg times negative h is just mgh. Okay? So that's the work that you did. So that is the work, that's the energy that the object gained from you, right? As far as you are concerned, work is, you're doing the work, you're losing the energy. For as far as you are concerned, your work is negative. Okay? And the amount of work you're doing, that's just the absolute value, is mgh. So work due to lifting is mg times h. Okay? So where did that energy go? It didn't become kinetic energy. You could say it became potential energy, gravitational potential energy of the object. So another way you could say the work energy theorem, if you have to take into account potential energy, is you can say the work would be change in potential energy plus the change in kinetic energy. Okay. All right. Now, in our case here, we're really more interested about with pressure volume work for most of the stuff we're going to talk about. Pressure volume work is energy change due to expansion or compression of a system against an external pressure. So the PV work is negative P external dV times delta V. Okay. To understand where that comes from, okay, force times distance, okay, What is the definition of pressure? Force per unit area, right? So if I want an expression in terms of pressure, what should I do? I divide by pressure and by area and multiply by area, right? Force per unit area is pressure. What's area times change in distance? If I have something like this with a cross-sectional area A and it moves a distance dx, what happened? That's a change in volume, right? So that's dV. Okay, so pressure volume work is defined as the negative of the external pressure times the change in volume, assuming the external pressure is constant. Okay? Now, the question is, why is it negative? That has to do with the sign convention, that if a system expands, it's losing energy, so work has to be given a negative value. Now, in older textbooks, okay, and I think chemical engineering textbooks still use the opposite convention, because work there is defined as the amount of energy that system is losing by doing work. So that becomes a positive number. Whereas in our case, that's the amount of change in energy by doing work. So that's a negative work. Okay? So if you are doing work, okay, if the system is doing work, we assign a negative value. Here's the convention. If system is doing work is done by the system, it loses energy. So we assign a negative value for W. Okay? Work itself, the magnitude is just the absolute value. But whether you assign a positive or negative value for it, it's just a matter of convention and not a matter of agreement. Pretty much all chemistry and physics textbooks have adopted this convention. Okay. So if that work is being done on the system, so exerting an external pressure on the system, okay, then work is going to be positive. Okay. So that's the formula for pressure volume work. And if your external pressure does change during a process, then you have to integrate. Instead of just using P delta V, you have to integrate P external delta V from V1 to V2. Okay, let's see if we get the right signs with this. What happens if your volume shrinks? Okay, minus P external delta V. If your volume shrinks, what's your delta V going to be? If delta V is negative, where W is going to be, pressure is always positive, right? Your overall work is all going to be positive. Negative times negative will be positive. System gains energy. If delta V is positive, your system expands. So this is strength, right? If your system expands as in response to an external pressure, against an external pressure, what's the work? It's going to be negative. Okay, so that's the reason for that negative sign in the formula. All right, so let's look at some examples. A sample of gas were to expand against a non-zero external pressure. What would be the algebraic sign of W? Negative. Good. Suppose the expansion of a gas results in an object being lifted. If the work due to lifting is 14.8 joules, what's the work for the gas? Negative 14.8 joules. So you have a gas. Here's your gas. It expands to lift an object, right? So it's going to push this thing up, right? Push up the object. So your gas, in order for your gas to lift the object, it has to lose energy. Okay? So what happens to your object? It gains gravitational potential energy. What about a gas expanding into a vacuum? Let's say you have a gas sample in this bulb right here. You hook it up to another bulb, and your other bulb has a vacuum, nothing in it. What's the pressure PV work for this? So you open this, what will happen? Okay, so PV work is going to be negative P external delta V. It's going to be expanding, right? So delta V is positive. What's our external pressure? It's expanding against nothing. External pressure is 0. So PV work is 0. Pressure volume work, in this case, is 0. It's expanding against 0 pressure. Okay, so expansion into a vacuum involves 0 work. How about this one? Against a constant external pressure, again, like I said, the formula is just minus P external delta V. P external is constant. You can move that out of the integral, right? So it's integral of dV is just V, evaluated from V initial to V final. So that's your formula for expansion or compression against a constant external pressure. What about a reversible What about a reversible isothermal expansion or compression of an ideal gas? Let's understand what it means when we say something, a process is reversible. Okay? We have a very precise definition of reversible in thermodynamics, which is not quite what you have in mind, what you would normally have in mind. So let's define exactly what we mean by reversible. When we say a process is reversible, you have to imagine a series of infinitesimally small steps. Okay? So, for example, let's say I have a gas right here. Okay? Let's say it's at 1 atmosphere external pressure. Okay? Let me just put a block here to represent the external pressure. Let's make that 2 atmospheres, okay? So you have a block that would cause the total pressure to be 2 atmosphere, and then you have 1 atmosphere from the air around it. And so you have a gas in here, okay? And let's say that this thing right here, let's call that a movable piston. Movable piston. That means it's greased, so it can slide easily, okay? So if there's an unbalanced pressure on either side, the pressure is not balanced on both sides, it will expand or contract. What would happen if I were to take this thing out? Suddenly, my total pressure drops from 2 atmospheres to just 1 atmosphere. So what will happen to my gas? My gas will expand, right? So that is what we would call an irreversible process, irreversible expansion. Okay? How can I make that expansion reversible? What I would have to do is so I still have that 1 atmosphere, right? Instead of a block, I would imagine, let's say, a pile of sand. Okay? Imagine a pile of sand, with the same weight as that block. Now, okay, for me to carry out the process reversibly, I take out 1 grain of sand at a time. So each step of the way, your pressure is going to drop by an amount equal to an infinitesimal amount dP, you might say. Okay, your volume is going to change by an infinitesimal amount dV. So I'll take out a grain of sand, okay, and I'll wait for equilibrium to be reestablished. Take out another grain of sand, wait for the equilibrium to be reestablished. So you carry it out through a series of infinitesimally small steps so that throughout the process you could say that the system is at equilibrium. Okay? Now, even when I'm doing this with just 1 grain of sand at a time, it's still not reversible. Strictly speaking, that's each one of those finite steps is an irreversible process. But to get the idea of what a reversible process, in other words, a reversible process is really an imaginary process. If you take an infinitesimally small change, do an infinitesimally small change in the external pressure, then you're doing it reversibly. Okay? So, in other words, throughout the process, you could say your external pressure, you're gradually dropping your external pressure. Throughout that process, the pressure of your gas is going to be equal to the external pressure. You're going to give your gas enough time to match the external pressure each step of the way. All right. So if that's the case, then you say that work is equal to negative of P external dV. That's our general formula for work. That's a general expression for work, right? But each step of the way, this external pressure is going to be equal to the pressure of the gas. So we are going to replace that by the pressure of the gas. So this expression right here is valid. Okay, this is equal to the work only if you're doing a reversible process. So instead of writing P external, you can actually write the pressure of the gas in your formula. But what's pressure of the gas for an ideal gas? PV equals nRT. How do I solve for P? Divide both sides by the volume. So here what I've done is I've replaced my pressure of the gas by nRT over V. Okay? Now, this is isothermal. That means every step of the way, I'm giving my gas enough time to equilibrate with the surroundings. Heat can flow in or out so that the temperature remains the same throughout the process. Okay, so T is a constant. I have a fixed amount of gas. So N, R, and T are constants that I can pull out of my integral. So I pull that out of my integral. What do I get? Okay, so what I have then would be, let me do the extra step over here. This is going to be negative nRT integral from V initial to V final of dV over V. What is integral of dV over V? It's integral of dx over x. Natural log of x. So this is going to be negative nRT ln V evaluated from V initial to V final. So that's the same thing as negative nRT ln V final minus ln of V initial, which is the same thing as negative nRT ln V final over V initial. Okay? And so that's the formula that we have right here. That's the pressure. That's the work due to a reversible expansion of an ideal gas. Now, since an ideal gas, a constant temperature for a fixed amount of gas, Boyles Law applies, right? Oops. Since Boyles Law is applicable here, this is isothermal, so Pi Vi must be the same as Vf Vf, right? They're both equal to nRT. So what's another way I could write this? Instead of writing Vf over Vi, what can I write here? Vf over Vi is equivalent to Pi over Pf. So I can also write it this way. Work is negative nRT ln Pi, initial pressure over the final pressure. Okay, so either one of these formulas will work. Okay, and you also need to realize that ln of x over y is the same thing as negative ln of y over x, right? If you switch your numerator and denominator, you're just switching the two things you're subtracting. So I can also rewrite this as negative as positive nRT ln Pf over Pi. Okay. Now to avoid confusion, it's best that you just remember the one of these formulas, and then you should be able to derive all the others. Okay. So that's the work due to an isothermal expansion of an ideal gas. Reversible isothermal. What if you have a van der Waals gas? A gas that obeys the van der Waals equation. Again, we replace P by our expression for a van der Waals gas. Okay, remember your van der Waals equation of state. P, what did we do? We had nRT over V minus NB, right? You subtract excluded volume, right? And then you subtract a correction term due to attractive forces. So that's the expression for P for a van der Waals gas. So you integrate that, and you'll get the expression. A and B are constants. Okay, so let's make that your homework. Derive the expression. Evaluate that integral. Derive the final expression. Yes. What if you're asked for the isobaric work, PV work for an isobaric expansion or compression? Reversible. What does isobaric mean? Constant pressure. Okay, so how can let's imagine physically how we might get this to happen. How can we get a gas to expand while the pressure is being held constant? Heat it up, but then if you heat it up, well, you put a movable piston here, okay? So even when you're heating it up, you can get it to expand. So your external pressure is constant, right? So what do I do to make this reversible? Let's say my gas is at 25 degrees Celsius. What I do is I put it in the oven, set the oven to 25.0000001 degrees Celsius. It's slightly warmer than the gas. So now the gas will heat up to 25.0001, okay, and then it will increase the pressure slightly, and so that piston will move, and so the gas will drop back down to the external pressure. But we always stay at the external pressure, basically. So you gradually heat your gas. So now that it's expanded, okay, while maintaining the same pressure equal to the external pressure, I crank up the temperature setting on my oven to 25.0000002, and so on and so forth. That's, of course, still an approximation. That's still irreversible, right? But the idea is you make infinitesimally small changes in your temperature. You gradually heat your sample, okay, so that at all times, while it's expanding, the pressure of the gas is equal to the external pressure. And at all times, the temperature of the gas is equal to the temperature of your surroundings. Okay, so it's at equilibrium at all times. That's how you carry it out reversibly. How would you carry this out irreversibly? You just stick it in the oven at whatever temperature you want so that it will expand. It will stay, the final pressure will remain the same. Eventually, it will go back to the same original pressure because you're maintaining the same external pressure. That would be an irreversible process. But if you let the temperature go up very, 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 very slowly, then you have an irreversible process. You have a reversible process. Okay? So your pressure is just going to be equal to the pressure of the gas. So you can just say that's equal to the P external. So whatever that P external is, that's going to be the pressure of the gas. I can use P there. So it's minus P delta T. That's going to be your work for that one. Okay. What about an isochoric process? What does isochoric mean? Constant volume. Okay, so I have a gas. Okay, let's say I were to heat the gas. What would be the work? And I fix this. I put a screw on this piston so it doesn't move. So volume is constant. work would be minus P external dV. And volume is constant, so volume goes from V initial to V initial. V final and V initial are the same, so what is this integral going to be? 0. No work done. So when you have an isochoric process, even if you do it reversibly or irreversibly, work is going to be 0. Okay? How about this one? Let's say you heat water from 4 degrees to 25 degrees Celsius. You look at constant pressure of 1 atmosphere. Okay? If you look up the density of water from the CRC handbook, okay, at 25 degrees you'll find it's 0.999973 grams per mil. And at 25, oops. Okay, one of these is at 25, the other is at 0. Okay, this is at 4 degrees Celsius. It's most dense at 4 degrees Celsius. Okay, so at 4 degrees Celsius, it's 0.999973 grams per mil. At 25 degrees Celsius, it's 0.997044 grams per mil. Let's compare W and Q for this. What's our Q? You remember how to calculate Q? Constant pressure. Integral of Cp dt. Right? You can look up Cp as a function of temperature. Or let's simplify it. We're just going to get an approximate value. What's approximate value for Cp? We're just going to take the average. So it's just going to be Cp times delta T. What's Cp for water? We're going to do 1 gram. Let's just do 1 gram. Okay, so Cp for 1 gram is 4.18 joules per Kelvin per gram, right? What's our delta T? 21 Kelvin. 25 minus 4. Doesn't matter. Delta T in Celsius is the same as delta T in Kelvin. So what's 4.18 times 21? Number? $87. So 87.8 joules. What's the work in this case? Minus P delta V. P external is constant. What's our external pressure? 1 atmosphere. Let's just take that as an exact number. What's our final volume? If you know the density of water, what's the volume? Density is mass over volume. So how do I solve for volume? M over D, right? So 1 gram, we'll take 1 gram as exact, over our density, which is how much? Our final density is 0.997044 mils. Okay, is that correct? Grams per mil. So, oops. So grams cancels out. Okay. And what's our initial volume? So this is our final volume. Our initial volume is 1 gram divided by 0.999973 grams per mil. So grams again cancels out, so that gives you the answer in mils. What's the answer here? negative 0.0029. What's the unit? Let's just do 3 sig figs. 291. 294. What's our unit? Milliliters times atmospheres. Okay. So let me just verify that. One sec. 1 over 0.997044 minus 1 over 0.999973. Okay. 2.94 times 10 to the negative 3 mils atmosphere. Okay. So what would that be in liter atmosphere? Milli means 10 to the negative third. So this is negative 2.94 times 10 to the negative 3, right? And milli means 10 to the negative 3 liters times atmospheres. So that's going to be negative 2.94 times 10 to the negative 6 liters times atmosphere. Okay, what's the relationship between liter, atmosphere, and joules? If you want to compare Q and W, we have to put them in the same units. What's the conversion factor? 1 liter atmosphere is how much? A liter atmosphere is 1.01, 101, right? 101.325 joules. It's 1.01325 liter bar. Okay, and 1 liter bar is 100 joules. So this gives you negative 2.94 times 10 to the negative 6 times 101.325 joules. And that should give us how much? Times 101.325. Oops. That's 0.298 joules. I've already changed it to liters right here.
Did you do that on that?
Oh, I did not? Okay. Yeah. Okay, so this is milliliters. I still have to multiply that by 10 to the negative 3, right? So the answer is 2.97 times 10 to the negative 4. Yeah, you're right. So 2.98 times 10 to the negative 4 joules. Negative 2.98 times 10 to the negative 4 joules. Okay. So which energy change is much larger? Work or heat or work for heating water from 4 to 25 degrees Celsius? Work. Volume hardly changed, right? So there's hardly any change in the volume. So you're looking at 88 joules versus 10 to the negative 4 joules. So you can pretty much ignore the work there. Okay. You'll see when you're dealing with gases, that's not something you can ignore. Work is not something you'd be able to ignore. But there's no change in the amount of gas, then pretty much you can ignore work. So it's convenient to just deal with heat and a lot of measurements that we do if we're not dealing with gases. Okay. Vaporization of water at 1 atmosphere. Assume you have an ideal gas for your water vapor. Assume the density of water is 1 gram per mil. Compare Q and W. Can you remember your Q? Would just be, let's just do 1 gram again. Let's just do 1 mole this time, makes it easier because I remember the value for delta H vaporization. So it's just be number of moles times delta H of vaporization per mole, right? So I'm just going to put a bar over that. So you have 1 mole times, what's the delta H vaporization of water? You remember? About 40.7 kilojoules per mole. Oh, by the way, before we proceed with that, going back here, did we have the right value for W, algebraic sign? What was our algebraic sign for W? Negative, right? Why negative? Should it be negative? Density is 0.99973. It dropped to 0.997044. So it expands. It's most dense at 4 degrees Celsius. So at 25 degrees it's less dense. That means it expanded. So expansion gives you negative work. Okay. All right. So go back to our problem here with vaporization. It's 40.7 kilojoules per mole. So your Q is going to be equal to 40.7 kilojoules. What's our W? Minus 1 atmosphere times delta V is going to be volume of the gas minus volume of the liquid, right? What's the volume of our gas? At 100 degrees, 1 atmosphere, what's the volume of our gas? Assuming ideal, what's the formula for volume of a gas? Ideal gas? And RT over P minus the volume of a liquid. 1 mole of water is how many grams? 18.02 grams. Assume it's a gram per mil, so that's going to be 18.02 mils, right? So volume of your liquid is 18.02 mils. So what's the volume of our gas? One mole times 0.08206 liter atmosphere per mole Kelvin divided times temperature of, so 373 Kelvin divided by 1 atmosphere. Okay, and from that you subtract 18.02 mils, right? So what would that be? What's our volume of 1 mole? So this is 1 mole. So mole cancels out. Atmosphere cancels out. Kelvin cancels out. So this will give you liters. So I have negative 1 atmosphere times this one in liters. .61 liters minus 18.02 milliliters. So that's times 10 to the negative 3 liters. You'll notice that the volume of the liquid is very small, right? Compared to the volume of the gas. In fact, in most cases, we can just safely ignore the volume of the liquid. When we're looking at processes where there's a change in the number of moles of gas, or there's a change in the amount of gas, okay, the delta V is just going to be the volume of the gas, the change in the volume of the gas. So this is a very good approximation that you can remember. You should remember delta V. Anytime there's gas involved, okay, it will just be delta V for the gas. You can ignore delta V for liquids and solids. Okay, so you can pretty much ignore this one. This one like this one right here, you can just ignore that. You don't have to in this case, but you know, in a lot of cases, it really won't make a difference as far as sig figs go. So what would this be? This is going to be 30.61 liter atmosphere. And you'll notice your atmosphere basically will cancel out. The value of your pressure will essentially cancel out here. Okay? So you can say then that delta V would be approximately equal to change in moles of gas times RT over P. Okay? So this is a good approximation for delta V. Anytime there's moles of gas, there's a change in volume of gas because of a change in moles of gas. Delta N gas times RT over P. That's your change in volume. So you can say your minus P delta V is approximately equal to what? Minus P times delta N gas RT over P. So your P cancels out. So minus P delta V would be approximately equal to delta N gas times RT. And remember last time I asked you to remember the value of RT at room temperature because the reason I wanted you to remember that is you're going to encounter that RT expression quite often. What's the value of RT at room temperature? It's about 2.5 kilojoules per mole, 2.48 or 2.5 kilojoules per mole. This is at 298 Kelvin, okay, approximately. So that's a good number to remember. Okay, there are other types of work. Let me just finish these last two slides that could be involved besides pressure volume work. One that you'll encounter would be electrical work. So that's integral of the potential difference, the voltage, okay. dQ is the amount of charge, okay, and amount of charge transferred would be just the current, that's charge per unit time, and then integrated over time. So VI dt, integral of VI dt, okay. So V is a voltage or electrical potential. A volt is a joule per coulomb. That's the energy gained by a 1 coulomb charge as it moves in response to a potential of 1 volt. That's 1 joule. Okay, so a joule is a coulomb volt. I here is current. Current is coulombs per second. Voltage times current is called power. So a unit for that is volt ampere or volt. Okay, and ampere is coulombs per second. A coulomb times a volt is a joule. So a joule per second is a unit of power. So that's energy per unit time, also known as a watt. Okay, so how much work is released to move 1 mole of electrons from the negative terminal to the positive terminal of a AA battery? What's the voltage across the negative and the positive terminal of a battery? Have you ever seen 1.5 volts? Okay. So that means what? If you have a mole of electrons, 1 mole of electron, what's the charge of 1 electron? 1.6 times 10 to the negative 19 coulomb per electron, right? Per electron. And a mole of electron is how many electrons? 6.022 times 10 to the 23rd electrons per mole of electrons. Okay. Oops. Uh-oh. So that's the charge. And what's the voltage? 1.5 volts. So that's how many coulomb volts you're going to need. This number right here, calculate that number for me. 6.022 times 10 to the 23rd times, this is 1.602 times 10 to the negative 19. That's okay, 96,300. Okay. I thought that was 96,500. To 3 sig figs. 1.602 times 10 to the negative 19. 6.022 times 1.602. Uh-huh. Okay, so it's 96,500. Okay, the exact value for that is 96,487. That's coulombs per mole of electron times 1.5 volts. Have you seen this number before, 96,500? In quant or electrochem in freshman chemistry. That's a Faraday constant. That's the charge of 1 mole of electrons, 96,500 coulombs. In the Nernst equation, remember your Nernst equation? Okay. That's the charge of 1 mole of electron. So multiplied by 1.5 volts, that gives you how much? Okay. So 1.44 times 10 to the 5th, 7, 10 to the 5th joules per mole of electrons. 444 kilojoules per mole of electron. And you can also have what's known as surface work, surface energy. Okay. Gamma, surface tension. Unit for that is newtons per meter. That's the energy needed to increase the surface area by 1 square meter. Okay, so the unit for that is joule per square meter. Now, that's the energy, that's the work that you need to expand the surface area of your sample. So if you have molecules in the bulk, okay, to bring them to the surface, they have to gain potential energy. And so the work that you need for that to happen, okay, is given by a property called surface tension. Integrate the surface tension over the change in the area. That gives you the work that's needed to change the surface area. Okay, so imagine you have a 1 milliliter spherical drop of water, okay, 1 mils. You want to split it up into 2 half-mil spherical drops, okay. Given the surface tension of water is 0.072 newtons per meter at 20 degrees, how much work would you need for that to happen? So this is half a mil, and that's half a mil. You're going to, the volume remains the same, but your surface area now changes, right? What's the formula for surface area of a sphere? 4 pi r squared. The volume of a sphere is 4/3 pi r cubed. Okay, so let's make that another homework assignment.